MBA633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll work a problem on hypothesis testing involving a population proportion, and it will be a one-sided test. So the problem setting is the following. We want to check if a population of pine trees has been infested with the bark beetle infestation. So a sample of 1500 randomly selected pine trees were tested for traces of the bark beetle infestation. It was found that 153 trees out of these 1500 showed such infestation. So at the 5% level, test the hypothesis that more than 10% trees have been infested. So you can see over here that the population we are dealing with here is the population of all pine trees. The population parameter that we're interested in, P, is the proportion of all pine trees that have been infested, and we're trying to do a hypothesis test on this. So the first step, of course, would be to set up the two hypotheses, the claim and the counterclaim. Again, following our usual procedure, whatever suspicion that we have that we're trying to confirm, if it is confirmed, we would like it to be the result of a rejection of the null, because of the way we do hypothesis testing in the way that we control for type 1 errors. So whatever suspicion that we want to confirm, if it is confirmed, we would like that to be the result of a rejection of the null. So what do we do? The suspicion that we have is that more than 10% trees have been infested. So if that suspicion is confirmed, we would like that to be as a result of the rejection of the null. So of course then I would make my alternate hypothesis be the the population proportion so P is greater than 0.1. That's how I set it up as the alternate hypothesis, because if that conjecture is confirmed, I would like it to be the result of a rejection of the null. That's why I set it up as the alternate. Since the alternate is P greater than 10%, my null of course has to be P less than or equal to 10%. That's the only thing that's left over, because the two together, H0, the null plus the alternate, must cover all possible values of the population parameter being tested. Now, since we're doing a hypothesis test on the population proportion, of course, the sample statistic that we would use is the sample proportion, which in this case is 153 divided by 1500, whatever that turns out to be. Okay. So we know that if the sample is large, then the sample proportion is normally distributed. So remember that all hypothesis testing starts off with the assumption that the null is true as an equality. If the null is true as an equality and the sample is large, then we know that P bar, the sample proportion, will be normally distributed. Its mean would be 10%, because that's what the null hypothesis is as an equality. And the standard deviation of the sample proportion would be P times 1 minus P divided by N square root. Notice that we're using P, not the sample proportion P bar. This is a very common mistake. We use the sample proportion P bar when we developed confidence interval for the population proportion. But when we are doing hypothesis testing, we used P. Why? Because all hypothesis testing proceeds starting with the assumption that the null is true as an equality. If the null is in fact true as an equality, then P would be 0.1, 10%. Okay, so we can check whether the sample is large. We would do n times P greater than or equal to 5. In other words, 10% multiplied by 1500 is definitely greater than or equal to 5. And then n times 1 minus P is 90%. 90% times 1500 is definitely more than 5. So these two conditions being met, I know that I'm safe in assuming that P bar is normally distributed. Given all of this, let's proceed and try to solve this problem both using the critical value method and the p-value method. You remember what the critical value method says. Critical value method says start with your level of significance. So I'm willing to accept a 5% chance of making a type 1 error. That's my level of significance. So my p critical What would I consider a really extreme value over here? It would be a position on the x-axis that's far enough away from the middle such that the area to the right, this yellow shaded portion, is 5%. Why the area to the right? Because the alternate hypothesis is p greater than 10%. So, of course, what I would use is the norm S inverse function to compute the critical value. So Z critical in my case here, not Z critical, I'm sorry. Yes, I could the critical proportion that I would use. Let me just erase this over here. So P critical would be equal to, let's see what value we get, equal to norm S inverse of 0.95. Now you recall why I'm putting 1.95, or actually you might remember it better if I simply put 1 minus 0.05. I want my right tail to be 5%, the yellow shaded area over here, and norm S inverse requires the area to the left to be specified as the input. So if the yellow area is 5%, the left area must be 95%. So I get 1.64. So any sample statistic that is more than 1.64 standard deviations away from the middle, I would consider extreme enough to be not to occur by pure chance. That's what I would consider. So let's see what the sample actually gives us. So the sample statistic that I have, actually I could use the symbol P or Z for that matter. Let's since the sample statistic is normally distributed, we'll say Z equal to 153 divided by 1500. That's the sample proportion that I obtained, 153 out of 1500 trees, minus 10%, divided by square root of 0.1 times 0.9 divided by 1500. That's the sample size. Okay, so that's the Z value. That's how many standard deviations away the sample statistic is. So let's see what value we get over here. So the numerator is equal to 153 divided by 1500 minus 0.1, which is equal to 0.002, and the denominator is equal to square root of 0.1 times 0.9 divided by 1500 is 0.0077. So divide one by the other, and I get 0.258. Okay, so the sample statistic that I got is only 0.258 standard deviations away from the middle. Okay, so this critical value is 1.64. Okay, and the value that I actually got is somewhere here, so it's not past the critical point. So I have Z, the standardized value that I got, the test statistic, is less than the critical value. So this guy compared to this fellow. Okay, so I cannot reject the null. So I would conclude by saying there's not enough evidence to conclude that more than 10% trees have been infested. Notice that I'm not going out on a limb and saying actually that the null is true. I'm saying there's not enough evidence to reject the null. Okay, there's not enough evidence to conclude that more than 10% trees have been infested. That is with the critical value method. Now let's see what we would get with the p-value method. With the p-value method, the question we are asking is, what is the probability that we would get a sample statistic of p bar equal to 153 divided by 1500 if in fact the null were true as an equality? So I want the probability of p bar being greater than or equal to 153 divided by 1500. That's the probability that I want to compute. And since the sample statistic is normally distributed, we know what Excel built-in function I would use, and that's the norm dist. This is equal to norm dist of 153 divided by 1500. That's the sample statistic. What is the mean? The mean is 10% because that is what the mean would be if the null were true as an equality. So it is 0.1. And the standard deviation, what is the standard deviation of the sample proportion? That is simply square root of 0.1 times 0.9 divided by 1500 with a cumulative of 1. So I end up with a probability of 60%. So there is a 60% probability. So my p-value is 60%. What's the physical interpretation of this 60%? The physical interpretation of this 60% is if the null were true as an equality. In other words, if the true proportion of bark beetle infestation was equal to 10%, then there is a 60% chance that I would get a sample proportion of 153 divided by 1500 or higher. Okay, so a very high chance, a very high likelihood, 60% probability that I would get this sample statistic purely by chance. So there is too high a likelihood that this sample statistic that I'm observing occurred by chance. It's highly likely that it would occur purely randomly, not because of the null being false. So I'm uncomfortable, highly uncomfortable rejecting the null in this case. So my conclusion is, do not reject null. Why? Because the p-value is greater than alpha. I'm willing to accept only a 5% chance of making a type 1 error, but what the 60% is telling me is if the null were true as an equality, there is a 60% chance that I would be observing a sample mean of 153 over 1500 or higher. That's too high a chance, is way higher than 5%. I'm not willing to take that risk, so I conclude there's not enough evidence to reject the null. Notice that in both cases, whether I use the p-value method or the critical value method, I end up with the same conclusion, that I cannot reject the null, so I cannot conclude. So the sample that I have here does not provide enough evidence to conclude that more than 10% trees have been infested.